So what I wanted to say something about, and you will find this information here from the lecture notes which we have for this week, is about scaling. And this is something which is important for project number 1 and for everything we do in machine learning. So one of the things which I mentioned during the lecture is this chapter number 4 in a textbook by Rashka, which gives you a good introduction to scaling. Now, there is another website which I really recommend. And that website is a website which I have linked in the slides here, or the weekly material. And that goes to Scikit-learn's website on scaling. And there are many, many different options. So let's try to look at some of them in connection with lasso, ridge, and ordinary least squares. So if you scroll down on the weekly material, the Jupyter Notebook, you will find a discussion of many of these scaling methods. And one of these links here, if you go to that one, you will find a discussion of one, which we will discuss in detail today. So what you can see here is first a general motivation of why you scale. Many of the estimators which we have, or the predictors or the features and so on, they are normally designed so that a specific feature takes value close to 0, or more importantly, that all features vary on a comparable scale. So you can have data which vary a lot. So if you're looking at housing data, so you can have, as the example which is used here, you can have one column which refers to the size of a room or the size of the house in square meters. And then you can have another column which refers to the number of rooms which you have. And when you scale this data, you have actually to be careful. It's pretty common that data are being scaled. So if you look at one of the most standard ways of doing it, which we will come back to, this is called the standard scaler. And this is often almost done by default by algorithms like lasso and ridge. And in that specific case, what you see here is that the standard scaler removes the mean value of each column of your features. So that means that this is something which is often done in case you have big variations in the data and you want to put them on some kind of common scale, but it's not guaranteed that that happens. So the scaling shrinks the range of the feature values, which you can see in the left figure here. And however, the outliers, the hope then is that outliers become less important. So this is one of the motivations behind these different scaling approaches. So this is the most, yeah. Yeah. So this is something we have to be careful. This is a very good question. And you will see immediately now, if we keep the intercept in the design matrix for a polynomial fit, we will actually have a column which is 0. So let's come back to that point. But this is a kind of standard recipe. And as you can see, I note in particular that because outliers on each feature have different magnitudes, the spread of transformed data on each feature can be different. So if we now go to polynomial fitting, which is the example which we have been dealing with, and which also becomes relevant for project 1 and the exercises we're dealing with. If you're using the standard scaler, some people say that, okay, you can reduce the impact of outliers, but it doesn't necessarily mean you're hoping that that can reduce the mean squared error, but it's not guaranteed. So in some cases, you may see no effect of doing the scaling. And then this is something which from the beginning, it may not intuitively be obvious whether it's a benefit or not. But it's a pretty common practice to actually scale your data in one way or the other. So let's take a closer look at the kind of data which we have. And I'm going to bring up the whiteboard here. So if you look at the data which we have, a polynomial fit. So we are setting up a design matrix with specific features. And each column, in our case, represents a polynomial degree. So we have a design matrix here, which has ones. And then we have x0 to the power of 1, x1, and down to xn minus 1. And then we have x0 squared, x0 cubed, all the way up to x0 to the degree of the polynomial which we are studying. And then we have x1 squared, and this goes all the way to x1 p minus 1. This is a kind of quantity which we are setting up and which you have already studied in one of the exercises, and we're going to play around, going to play with this again and again. Now, one thing you see here is that if you now look at your data, what you would have is obviously data in project 1, and in many of the exercises, the weekly exercises, we have x, little x, which is set up in terms of a uniform distribution between 0 and 1. Now, what you will see here is that if you scale the data by the standard scalar, since you have x to the power of something, and since x now is defined between 0 and 1, what will happen then is that the higher powers of x will become very small. So that means that you will have a very small mean value. And that means that you could get columns here which have very small values when you subtract the mean. So these are things to think of when you are using some of these standard recipes, okay? So it's not given that if you do the scaling, as you see in basically all textbooks and on the scikit-learn library description of these codes, that you will automatically get a better result when you fit the mean, let's say when you fit the mean square error. So in a sense, it's you who has to look at the data you have and try to understand what happens. You may have other type of data where you can have one column here which represents the wind direction, another column which represents the pressure, and then you could make things dimensionless because things often come in units. So you could try to make them dimensionless and also scale it, because when you are inverting these matrices in standard linear regression, where we now have beta, the optimal value, which is given by this matrix, x transpose times x minus 1, x transpose times y, we have a matrix inversion problem. And if the numbers are very small, this can sometimes lead to round-off errors, or if you have large differences between the numbers, this can lead to round-off errors and loss of numerical precision. So it's not given beforehand that you can get a better fit because you saw that you had some outliers. So it's you at the end, it's actually you who has to look at the data and try to figure out what could be the best strategy. Now, the other thing, which was a question from the audience here, is what happens when we take away the mean value. So the standard scalar, which you see in scikit-learn, what it does, it takes the mean value of each column and subtract the mean value. But then you see that the mean value here is actually something which gives you a 0. And if you have a column with 0, if you subtract the mean value from this column, a column with zeros will give you serious problems if you try to invert this matrix. So this is also something to think of, and that's why many practitioners, when they make a fit in linear regression, they leave out the intercept. I mean, you may have a problem, or you may have problems where you don't need to consider the intercept. But you can recover the intercept by some simple algebraic manipulations. So let's look at that. So you see now, if you want to use the standard scalar, which you have in scikit-learn, and many people use that one almost by default, then you have to be a little bit careful, because if you're now setting up the problem yourself, you can risk having matrices which have zeros along the column. Now, scikit-learn does normally not include it by default. Okay? So let's just look at how you can recover the values of beta 0, because what we have in these different projects, we have a model where y of I is given by some polynomial approximation, beta 1, x of I plus beta 2, x of I squared, etc. Now, if you now look at a simple fit which we are doing with the cost function, so this cost or loss function is given by the mean squared error as a function of beta. And in that case, this is nothing but 1 over n. So let's just quickly repeat it. And then we have an I equals 0 to n minus 1. And then we have a y of I. And then we have the sum over j equal 0 to the number of features of xij multiplied with beta j squared. And what we are doing is to take the derivative with respect to the different parameters. And if we take the derivative with respect to beta 0, we see quickly then, when we do the calculations, that this gives us minus 2 divided by n. There is no x in front of beta 0. And then we are left with a sum from I equals 0 up to n minus 1, y of I. And then I have minus beta 0. And then I have the higher order terms, which go like minus j equal 1 to p minus 1 of xij of beta j. So let's just, for simplicity, assume that we have made a fit which is a straight line. So this is beta 0 plus beta 1 times x of I. Let's just make that assumption. Then, if you look at this equation here, which we want to drive to 0, what we get then, when we multiply away the factor of minus 2 divided by n, so I'm just multiplying this factor away, what I have then is a sum where I have I equals 0 to n minus 1, and then I have y of I minus beta 0, minus, and now I put only one coefficient beta 1, so that means that what I'm getting is an x of I of 1 multiplied with beta 1. And we want this one to be 0. So this is linear regression in its simplest form, with just a straight line. So when you're playing around with these different kinds of scaling functions, either you write it yourself or you use scikit-learn. And normally what we recommend is just to use scikit-learn. In the projects, you should feel free to use these functionalities which are baked in. In the lecture notes for this week, you will see how you can do it yourself so that you know exactly what is going on inside the black boxes which scikit-learn provides you. This is a little bit of the demystification which we want to do in this course. But many of these functions are actually, how to say, ready-made for you. And when you have understood what happens inside, in a way, there is no point in you rewriting this again and again, because it will give you a lot of clutter in your program. So it will just make your program longer, and sometimes it can be more difficult to debug. But you should feel free to use these programs as you want. But when you use them in the projects, you should cite them. So we will actually, if you don't cite libraries and software you used, we will deduct points in the final project. So this is actually about the correct way of dealing with the scientific results which have been developed by other people, because else we give the impression that we have cooked up everything ourselves, right? So if you look at these calculations here, now what we can do, we can simply isolate beta 0. So if we isolate beta 0, we have a sum of I equals 0 to n minus 1 of beta 0. Beta 0 is just a constant. So this becomes simply n times beta 0. That's the number of variables which we have. And that is equal to the sum of I equals 0 to n minus 1 of yi, the data which we have, minus, and then I have a sum over I equals 0 to n minus 1 of xi, 1. And then this is multiplied by beta 1, but beta 1 doesn't depend on the variable I. So I can put that one outside here, beta 1, like that. Okay? So this is just to tell you how you can recover the intercept, even if you don't include it in the fit. So typically, if you run scikit-learn without saying anything, it actually does this by default. So if you then try to print the coefficients which you get from the fit, it will not print the intercept. You have to ask for it explicitly. Okay? So what happens then, we divide by n. So we have beta 0, which is the intercept, is 1 divided by n, and I equals 0 of n minus 1 of y of I, minus just this constant beta 1, which we obtained from the fitting, I equals 0, n minus 1, x of I, 1, and this is divided by n. So this quantity which you see here, that is the sample mean value. So you have a sample of data, and that is the average value. So this means that this is something you can calculate. So we write this as mu of the data y. And then we have minus beta 1. And this quantity which you see here is actually the sample mean of column 1, or column 2 in this specific case. So if you look at what you have here, this one, and you divide by n, this is nothing but us going back to the design matrix and summing up all these components and dividing by n, and that gives the mean value of a given column. So if I sum all the numbers here or here, that gives a mean value for all columns. So that means that what I get then is just mu, which I define as the mean value of x. And now I'm going to put x1 here to indicate that that's the column with x to the power of 1. So when you have done the fit of the betas, and you can do that fit without the intercept, so you can leave out the intercept column. When you do that, then you have the value of beta, and these are quantities you can calculate, and then you have immediately the value for the intercept. So that means that you would then do the matrix inversion and everything without this column here. And it's pretty common to just leave it out. You can keep it. For ordinary least squares, there is no difference. The difference comes in when you want to do the calculations with ridge and lasso. And we will try to see why it becomes then important to leave out the intercept in the optimization of lasso and ridge. So if you now go back to what we discussed in the lecture yesterday, if we go back to ridge regression, in that specific case, what we have is that the C of beta is given by the mean squared error of beta plus this parameter lambda, which we wrote in a compact way as the norm 2 of a quantity squared. So what is the norm 2 of vector? Let me just remind you of that. The norm 2 of vector is actually given by this specific term, v0 squared plus v1 squared, and up all the way to the last element, vn minus 1 squared. And you would typically write this as a sum over I, and then we have v of I squared, and then you would simply put the square root sign. So when you square it, then it's clearly v2 norm 2. This is also called it has a name in mathematics. You probably have seen it. So one is, it's called L2 norm, but it has another name which you probably have encountered. Does anyone remember that? It's named after a famous Greek mathematician. And this was a guy who lived 300 years before Common Era. The name begins with E. Anyone who remembers that? Euclidean norm. That's one of the other names you've probably seen this quantity defined as. I actually tried to learn Greek by reading Euclid. I gave up, obviously. I had a translation in another language, but yeah. This is my attempt at writing the letter V. Sorry. So this clearly means that we simply have V squared, V0 squared, and V1 squared plus Vn minus 1 squared. And we can also rewrite the mean squared error in this very compact way. And this is a way which you will see again and again in the course here. So we would have y minus this design matrix times beta. And then we have norm 2 squared. That is another way of writing the mean squared error, which you will see me using again and again because it gives a very compact notation here. So this is ridge regression. Now there is an important thing which happens here when you do the ridge optimization. The thing now is that if you include the intercept here, the intercept can be a large quantity. You will often see that many of the other quantities here can be small. So if we have the intercept, there can be a bias on the first term. So it means that in the practical implementations of ridge, so it's normal in ridge optimization, to not include beta 0 in the optimization, in the calculations. So that means that if I now set it up, I would have a cost function which looks like this, 1 over n, and then I have my standard mean squared error, and I have a y of I minus, and then I would be summing from p equals 1 to the last one. And then I have the design matrix multiplied with beta of j, of j here, squared, plus lambda, and I sum from j equal 1 to p minus 1 of beta j squared. So what happens then, because if I make lambda large, as we discussed yesterday, we are suppressing features. But what could happen then, because in many cases, the intercept can be a large number, but we don't know that. But in many cases, it can be. And then you would put a heavy emphasis on the beta zero term if lambda is a large number. So you want to avoid that one when you're doing the fitting. And that means also that when you do the fitting now, you don't put an emphasis on that. So you should try to make the fit with and without the intercept, because you can run it with the intercept. I mean, there's nothing which hinders you doing that. And it's useful then to test the final mean squared error you get after the fitting. So you run the fit with or without the intercept. And what will happen in many cases is that without the intercept, you may get a better mean squared error. And what you would also have done then is, when you take away the intercept, is that you have scaled your data by subtracting the mean of every column in the design matrix. Okay? The same thing applies to lasso. So the same for lasso. Except that for lasso, what we have is that we have a cost function, which is given by the standard mean squared error of beta. But now we have plus lambda, and we have j equal 1. We leave out the intercept again, but now we have the absolute values of the betas. And this quantity, which you see here, is normally called the norm 1 of a vector. And we put a 1 in here. Now, in these optimization calculations, you are not limited to these type of forms. You can have other types of norms if you want to, but you can also add other functions. So this kind of term which you see here, this kind of penalization term, as we called it, or regularization term, introduces a new parameter, and you're going to play around with that parameter and try to find the parameter which gives you the best mean squared error. Because at the end, after you have optimized this problem, you're going to calculate the mean squared error or other measures for testing whether your data or your model is giving a good fit or not. So at the end, when you've done this, you would calculate just the mean squared error. And that is the way you assess the quality of your model. You can calculate the R2 score or other quantities. Yeah. Yes, yes, correct. Yeah. So lasso is an L1 norm. So we would call this an L1 norm. Whereas ridge is normally called an L2 norm. But the thing is that if you look at these functions here, this is not limited to linear regression. When we are going to deal with neural networks or decision trees and so on, you can actually add such a term. So what you're doing in principle is just to optimize another function. And in some cases, with these additional degrees of freedom, you get more flexibility to fit the data. But it's not given that you will get a better fit. So in principle, you may not know what gives the best solution. In general, what you would have could be a function for regression. We'll have a cost function, which now includes the mean squared error. So I'm going to write this in the compact way, the norm 2 of the mean squared error. But I could also add another term if I want to. I can make it more complicated. And I can look at the absolute value. I can just look at the norm 1 as an expected value. And then I can add these other terms a regularization term where I have this beta, and then I just put a p here, or let's just put a number L, just to indicate that this L can be 1, 2, 3, or infinity. So these are different types of norms. And it's actually you who decides what kind of function you want to use. The reason why we stick with the mean squared error when we did regression and ordinary least squares is that we get nice analytical expressions. Okay, so that's essentially the reason. If you now include the absolute value or the absolute difference, this is something which you could use in case you have outliers. So you could have a test then that if my function here has some values which are largely different, then I'm using this function. And if I don't have any outliers, I just use that one, because this one, as we discussed last week, emphasizes outliers. So if you have many outliers, that means bad fits, then clearly this will blow up. So you could think of you being able to look at your data, and then you would say, okay, for some data, I'm going to use this one. For some other data, I'm going to use that one. And then I have, in addition, this regularization term. So this is pretty common in machine learning to mix actually different types of function in the optimization. When you've done the optimization, then you go back. So you find a beta optimal, which in our case means simply that I have a y tilde, which is given by x times beta optimal. That's the model I have made. This is the function I am optimizing here. Actually, this has a name. It's called Huber, loss function or cost function, after a statistician called Huber. And then you would calculate at the end the mean square error, but you would calculate it with beta optimal. So this is the number you would present in your report after you've done all possible manipulations. And just keep in mind, there is no kind of often no kind of a priori how to say indication whether this type of data will benefit from scaling or not. Now there are other types of scaling which if we now go back to this scikit-learn function, so let's just go back here. So that should be my, where did I put my, here we are. So the standard scaler is one of the most used ones, and it's almost done by default. So sometimes you do have experimental data on the standard deviation and the variance, but normally we would just put the variance to 1. This is pretty common. So you can see here, it removes the mean and scales the data to unit variance. Then there is another one which is very much used, and this is the min-max scaler. So in the project, there is a question on, should I scale my data? So you have to reflect about what kind of data you have. In the first part of the exercise or the project, the x values go from 0 to 1. So in a way, they are already put into a min-max domain. There is no variation between x and y. They take the same values. So you are going to deal with a two-dimensional function, the Franke function, which will depend on x and y. So which means then that in that specific case, the x and the y values, there's no need to use a min-max scaler. It means also that when you look at the polynomial fit, you have to be a little bit careful with high order degrees of the polynomial, because if x goes from 0 to 1 and y from 0 to 1, you can get values in columns which are very small. So these are all kinds of things you need to think of when you look at the data. exactly. So the other thing is that the function itself, which you're going to look at, doesn't differ that much. It goes from some 0 to some values of plus 9, plus 4, or something like that. So it's a function which also doesn't differ by orders of magnitude with the input variables. So in a certain sense, what you could say is there's almost no need of doing the min-max scaling. And as you can see here, these are very sensitive to the presence of outliers. So be always careful with these things and take a look at these functions. There is also a max upscaler, there's the roboscaler, and there's also other types of ways to scale your data, which then clearly will depend on the type of data you have. So in project one, except for the topographic data, our data are pretty boring, really boring. In the sense that X and Y go from 0 to 1, and then the final function takes just values in basically almost the same range. So the function which we are going to deal with in the project, so if we go back to that, I should have it not here, but let me just bring it up and then we stop here. So if you look at the project, you can find the project in this folder on projects. I invite you to take a look at also the files which we have on project writing. And these are things we want to discuss with you. There is a reason for why we enforce this kind of way of handing in the reports. We will talk a little bit more about it, but one of the reasons is that many of you have not written a scientific report, and it's a very good training for or preparing you for your master thesis writing. Because a master thesis is essentially a technical report. There's also a set of files here about the way we grade the projects. So take a look at that. If you forget the references, we penalize you. We just subtract 5 points. So for the first project, since many are not familiar with writing projects and not everybody reads the guidelines, then we tend to be a little bit more lenient in the sense that, hey, you were missing the references, please upload a new version. So we don't tend to penalize you in the first one. But if you haven't learned it after the first one, then we are a little bit harsher in the second and the third one. But this is more to get you started with project writing. So take a look at that one because that's the rules of the game and the way you will be graded. And the way we also produce the feedback. Now, if you look at the project, you have different versions of it. You can, there's a LaTeX version, there's a Jupyter notebook, and there's a standard PDF. But I just wanted to bring up the function here and say something about, so this is the function we are going to fit in the beginning. So it's a series of exponentials. So we can make a polynomial fit in X and Y. However, when you start developing the codes, try to use the exercises for this week and next week because it's simpler. So when you have the machinery functioning in one dimension, it's easier then to just include another function. So try to break down, and we have some recommendations here, just try to run everything as you do in the exercises. Because the only thing you will need to change then would just be the type of functions and the type of polynomial which are fitting. Sometimes we always want to, or rather, we always want to do the interesting thing first. We are impatient as humans, but sometimes that can lead to some errors which can be difficult to find. So if you feel a little bit uncertain, just start with the simpler one-dimensional functions. And there is also an example here how you can set it up. This is actually called a Franke function. And it's one of these many functions which are, how to say, not the easiest ones to fit with a polynomial approximation. You will find a reference to other ones if you're interested in the report here. There is a link to more complicated functions, which I think I put in. I think I put the link somewhere here. Yeah, let's see. I may have. Yeah. So there is an article here which lists a series of functions. You can actually find online many functions which make life difficult for linear regression. Now, there's a reason why we take this function, because it looks like a landscape. And the final data, which we have, are topographical data, which are set up. You can actually set up the data by going to this website. So it produces a TIFF file, which you then have to read in. And we have some instructions on how you can read it in. So the data we took were from some landscape in Norway. But if you feel homesick, you can actually go back here and download the terrain from where you are from and try to reproduce that. And if you like to live in the flatlands, then it's, yeah, you could take some data from the Midwest or one of our neighboring countries. I think one of them is called Denmark. Okay. So this is the type of things and which we will work with. And the first parts here are actually things which should follow from exercises, the exercises this week. Then there is a paper and pencil part, which we will discuss in the lectures next week. And that will be part of the exercises in week 37. So gradually, everything you do in the weekly exercises are things which go straight into the project. Okay? So take a look at things and also when it comes to scaling, try to both look at the examples which we have in the slides here. So you will find the examples which we went through in the class, which are here, and the examples with and without the intercept. And at the end, we normally recommend just using the functionality of scikit-learn. So scikit-learn is an extremely nice library. It doesn't contain advanced deep learning methods like convolutional neural networks, recurrent neural networks, but all these functionalities like scaling, test, train, splitting, and later when we come to k-fold optimizations and so on, they're just baked in there and use them because they also interface well with all the other libraries like TensorFlow and PyTorch. So that's why you will often see in many textbooks in machine learning that they actually refer to scikit-learn. So the book by Rashka is called Machine Learning with Scikit-learn and PyTorch. He has actually written another book, which was PyTorch has been replaced with TensorFlow, etc., etc. Okay. Any questions to the projects and the exercises? So try to use this manual pages of scikit-learn, especially this one, which we link in the project. So you will actually find that in the project and where they actually discuss the pros and cons of scaling. And this is something you will have to play with. And it's not given that you will get a better result with and without. Just one small thing, as we mentioned in one of the lectures, we do normally recommend when you're writing the reports, because many of you have never written a report before. English may not be your native language, so feel free to use ChatGPT or similar tools in, let's say, writing the introduction, get inspiration, but then we want to have you to cite that you've been using these tools. If you use library functions from scikit-learn, you should cite that. And there are examples on how you can cite it. All these libraries, they actually have a citation recommendations. So try to use those. And if you use ChatGPT, one of the things we would like you to include as supplementary material is actually the conversation you've been having. So you can ask ChatGPT, what is linear regression, et cetera, and use that to write an introduction. We would like to see that conversation. Because then we can see how you have digested the feedback. So one important thing is obviously that what it gives you can contain errors. It's not precise. It's getting better and better. But that means that you is the one, again, who has to gauge whether this is good or not. And that means that you have to develop a deeper insight about the topics. But it is a very useful tool. We are not going to run these projects through any kind of plagiarism or ChatGPT test or anything. So when you hand in the report, we are not going to do that. So we do trust you guys. Okay? I'm going to stop here now.